Hello. In this lesson, we're going to talk about one-to-one function. Okay, before we talk about one-to-one function, we like to recap on the definition of function, right? We went over this concept in the previous video, that a function is a rule, right? It's a rule that assigns to each element x in the set of A exactly one element called f of x in the set of B. And here we talk about the notation that x is the input and the rule applies to the input, and we have talked about the domain, which is all input such that the rule could apply, and for each application it produces exactly one output. And of course, range is all possible outputs produced by applying the rule of the function to each input in the domain. So a function is a rule, right? We have this shorter version of the definition of function where we talk about, the number from the domain is called input, the number in the range is called output. Okay, so in short, when we address function, we talk about the rule. And the rule determines what can be in the domain and what cannot be in the domain. And it also determines the range. So domain and range is a natural thing we'll be asking, if this is the rule, what is the domain, what is the range, right? We went over examples. Vertical line test. Some of you might have learned this before, but I'd like to review this piece, because if a graph is given, how to decide if the graph represents a function. Representing a function meaning for each input, there's exactly one output. The wording for vertical line test is we draw vertical lines arbitrarily across the graph. No vertical line passes through the graph more than once. If that is so, we call it passes the vertical line test. Otherwise, okay, it doesn't pass the vertical line test. If a graph passes the vertical line test, that graph represents a function. If a graph does not pass a vertical line test, it is not a function. Okay, so all of these functions we talk about, they all passes the vertical line test. Okay, you just draw a vertical line arbitrarily. For example, we take an example, right? Just to recap this concept. Suppose we draw a vertical line arbitrarily, right? You can draw as many as you want. Any one you draw, it crosses the graph at one point. Suppose it crosses over here, okay? So that's the crossing. The crossing is a point. This point tells us for input as such, there's exactly one output. If it is a function, okay? And it is true for any arbitrarily drawn vertical line, and this is true. You always touch it no more than once. If it's more than once, it failed the test, it's not a function. So we got that, right? So now we're gonna talk about the horizontal, the one-to-one function. One-to-one function. What is a one-to-one function, right? A one-to-one function, first we have to start with a function, right? Only for a function, we start to see, oh, is this one-to-one? So to be a function first, it's essential for us to consider it is one-to-one or not, right? In other words, only functions are possible candidates for a one-to-one function. Now, suppose we have a function f, right? It's a rule that assign each input from the domain, exactly one output in the range, right? So we know that exactly one output for each input. Now, if this function is also called a one-to-one function, we have an additional requirement. And this is the additional requirement. The additional requirement says, if no two inputs of D have the same output, that is to explain what it means by no two inputs have the same output. That is for any inputs, whenever you have any inputs from the domain, okay, x sub 1, x sub 2, they're both from the domain. They're both from the domain. Okay, of course, they're not the same, and their respective output are not the same either. If this condition is satisfied for any two arbitrarily chosen inputs, then it is a one-to-one function. Okay, so for input x1, we have an output f of x1. For input x2, we have an output f of x2. So whenever the two inputs are different, the outputs are different as well. If these conditions are satisfied, it's a one-to-one function. So let's look at some examples, right? The first example that the constant function we have done last section, or a function f of x equals to 2. We talk about the rule of this function. The rule of this function basically says the domain is all real numbers, right? Domain is all real numbers from negative infinity to positive infinity, right? And we chosen a element, right? We chosen an input from the domain, lowercase. Okay, and apply the rule. And what is the rule of this function? The rule of this function says any input you give me, right? The output I produce will be 2. And the range, of course, we know the range. Okay, it's in the range. It's in the range, which is 2. Is this a one-to-one function? Obviously, it is not, right? But when we make the statement it is not, we have to give one case that violates the one-to-one function requirement. In other words, what is the opposite? What is the opposite of a one-to-one function, right? What is not a one-to-one function? Not a one-to-one function, suppose it is a function, it's going to violate this statement, right? So what is to divide, what makes the violation of the statement? How many times the statement needs to be violated? Well, we talk about mathematical truths. If true, it's always true. False once, false. Okay, so since it violates, it only has to violate once. Okay, so what is that violation? That violation, it will be that it's violated. Okay, the inputs, the outputs are the same for some inputs that are from the domain. So this is the definition for not a one-to-one function. I know this might be a little bit difficult for you to understand, but try, okay? You may want to pause the video sometime, from the process of watching. You really need to understand this. So we're going to apply this in this situation here, because for a function not to be one-to-one, I don't need to demonstrate, oh, for every different for any pair of different input, the output are the same. Even though it is true in this case, we really just need one case. Okay, so when you answer this question, all you have to say is, no, it is not a one-to-one function, because for input 0 and input 1, the inputs are not the same, but their outputs are the same. Okay, the outputs are the same. So the violation, it doesn't have to violate 10 times. It only has to violate once. So false once, false. Therefore, this function is not one-to-one. Okay, so next one, right? I chose this function. Is this function one-to-one? Well, to demonstrate it's one-to-one, we just have to make sure this statement is true. If this statement is true, it has to be true to be a one-to-one function. Now, okay, this, of course, we understand the domain of this function, right? The domain of this function is, we choose the input domain x1, x2. They belongs to the domain which is from negative infinity to positive infinity. Okay, so whenever x1 are not this, x1 and x2 are not the same, what is what is x1? F of x1, the output is x sub 1 to the power 3 and the other output will be x sub 2 to the power 3, right? So when the inputs are not the same, you raise the power 3 and they're still not the same, right? So you will say, so the way you can say this, okay, you must learn how to do this, okay? You say it is a one-to-one function because these two are the outputs. The outputs are not the same whenever x1 is not the same as x2, because these are the input, output, input, and output. And the statement we made here certainly is true. Okay. The next question comes is that, is there a graphic, test, right, such as a vertical line test, right? For vertical line test, we use vertical line test to test if a graph is a function. Do we have a line test for a one-to-one function? The answer is yes. We actually have a horizontal line test for one-to-one function. Why horizontal line test, right? So first of all, what is horizontal line test? What is a horizontal line test, right? A horizontal line test, what does it do, right? What is a horizontal line test? Horizontal line test is that if we're given a graph, right, it passes the vertical line test already. Okay, if it passes the vertical line test already, then we go about to see vertical line test, horizontal line test. So we're going to draw horizontal line arbitrarily. If, okay, if any horizontal line, any horizontal line passes the graph no more than once. And that then the graph passes the horizontal line test. If it passes the horizontal line test, then it is a one-to-one function. A one-to-one function. Okay, in the previous two examples we did, right? We are pretty familiar with about these graphs, right? So let me bring the graph that we did, you know, from before. We have the graph. Where's our you know, cube function, right? Maybe I shouldn't be doing this. Okay. Cubic function right here, right? Cube, x to the power 3. Okay, x to the power 3. It already passes the vertical line test. It also passes horizontal line test, right? So let's draw horizontal line arbitrarily. So suppose I'm drawing this horizontal line. Okay, you can imagine I draw as many as possible. It crosses the curve once. None of them crosses more than once, right? You can draw as many as you wish. It's hard. It's, you know, it passes the horizontal line test. And this point tell us, what does it tell? Let's see what it tells us, right? For this output, right? For this output, oops. I'm going to erase this. Whoops, it erased all of it. Okay. All right, so for this horizontal line, I draw here, right? There are all these different, it crosses exactly once. So at the crossing, it says for this output, okay, for this output, there's only one input for it. There's only one input for it. So for this output, there's only one input. There's not, if I put another, so suppose there's no other input will give us exactly the same output. There's no other inputs that will give us exactly the same output. So that is saying no two inputs that produces the same output. Okay, no different inputs that produces the same output. Okay, I hope I made myself understood. Okay, now, so that's how we draw the horizontal line. We draw the horizontal line. The horizontal line determines the output, right? How high it is. For this output, there's only one input. There's only one input and one input only. Okay, so let's look at another example. Okay. And this other example I'm going to use f of x equals to x squared. Okay, we are pretty familiar with this function. Okay, so I'm not going to dig to the past to graph it. Everybody knows this function. Okay, so I'm making some adjustment to the graph. And that's the graph. That's the graph. It passes a vertical line test, all right? Does it pass horizontal line test? Say if I draw a horizontal line arbitrarily, what does it say? Okay, it says for this output, right? For this output, for that output, you know, this is the output. Same output, but there are two different input for it. There's an input here, right? And there's also an input on the other side. Okay, so different inputs, same output. That's the violation of the definition of one-to-one function. The definition of one-to-one function says for different input, the output must be different. Okay, so now we know that doesn't pass horizontal line test. How do we speak the sentence? How do we say it, right? From now on, you are taking math classes. You can't just say, oh, it is not, it is yes. You have to learn to use the language of mathematics to make your case, So when you say this, you have to cite the definition. So this is how I'm going to cite the definition, okay? Because the violation only has to happen once, right? So you can just give some examples. For example, I would say, okay, I'm just giving you an example, one way of saying it. Then you say it is not a one-to-one function because, okay, f of -2 or -3, I type -3, is the same as f of 3. That's it. Okay, that's it, actually, you're done. Because in this notation, right, f of -3 is 9, right? You plug in, you get 9. F of 3 is 9. So obviously the reader can tell that the inputs are different. -3 is different from 3, but their output are the same. By saying that, you're finished, you're done. You can see I actually have cited the definition. I've cited the definition, right? Even though, I was just drawing the picture arbitrarily, I only need one case to speak the language where I cited the definition. Okay, so here I have cited the definition and the opposite of the definition, right? The opposite of the definition. I have cited the opposite of the definition right here. Okay, so I'm going to put it at note. This may not be something you're quite used to, which is using words, using definition to make your case, but you must start learning this, right? The input are specified, and that one sentence is sufficient. Of course, you have many, many examples. You can also change the structure of the sentence, right? Or you can also say since, right? You can use since, right? Since f of -1 is equal to f of 1. You can use different examples, right? If you want, you can use fraction, decimal, right? Since this is true, and thus it is not a one-to-one function. You see, that's how we can express it. Okay, so this is about one-to-one function. Let's do, what can we do about if a function is not one-to-one, right? So sometimes a function is one-to-one, great. If function is not one-to-one, so what can we do? If there's anything we can do about it, right? So this function is not one-to-one. How can we do something about it? Is there a situation that we want to do something about it? Okay. One of the techniques that we're going to learn in this semester about trig function is this technique, right? Sure, this function doesn't have that one-to-one function property, but I really do want to have a one-to-one function. So what do? There's something called truncation. Truncation. What is a truncation? Truncation means that you're gonna modify the function. We're gonna modify the function. How do we modify this function so that we make it one-to-one? Well, one of the ways, I'm not saying this is the only way, is I can chop off this piece. By chopping off this piece, right, I get rid of the domain on this part, the negative number part. Okay, so the consequence of this truncation is I'm creating a new function, and this new function is f of x is equals to x squared. It's still the same rule, but I'm going to make a restriction because I truncate, I cut it off. Okay, I cut this piece off, cut off. Okay, by cutting this off, what does that mean? I'm restricting the input to be only greater than or equals to 0. Okay, so what do I have now? What do I have now? As a consequence, I have a new function. Okay, so my new function just one piece. Okay, so this function then passes the horizontal line test. So this new function, so remember, this function here, this function is different from this function. They have different graph. Why they're different? Well, they have different domains, right? So in this earlier function, even though they have the same rule, right? The earlier function, it has the same rule, but the domain is all real numbers from negative infinity to positive infinity. Okay, we consider these two functions different because they have different domain. This latter function actually has an inverse. This latter function has an inverse. This latter function is one-to-one. It has an inverse. It has an inverse. Okay, so why do we talk about one-to-one function? Right? Why do we talk about one-to-one function? Because every one-to-one function has a unique inverse. And we want to find that inverse. So that will be the topics for next time. Thank you for watching. Stay tuned.